Welcome everyone to the Hamlyn workshop on surgical robotics research. Pleased that over 30 have already joined. The number keeps rising. So this is a workshop on surgical robotics research performed with open research platforms. Raven and dVRK, or DaVinci Research Kit, are two well-known examples, but the workshop is actually going to have other systems as well. So that's one of the things that you'll learn about is the open platforms available for research, but really focusing on the type of research that can be done with these platforms. So let me get things started. We have 6 presentations from members of this research community. And so the first presentation will be given by Jing Huang from the Chinese University of Hong Kong. So I'll turn the screen over now to Jing.
Sorry, you are still muted.
Okay, can you hear me?
We can hear you, yes.
Okay, okay, I see that's good. Okay, I will start my presentation. Hello, everyone from the screen. This is Jing, a PhD student from the Chinese University of Hong Kong, and it's a great pleasure to share our work on non-fixed contact manipulation control framework for deformed objects with active contact adjustment here, which is also a joint project with our collaborator from Jeju. So first, we simply introduce the background of our work. So it's notable that the deformed objects manipulation has continuously attracted attentions from the robotics community these years, and one widely adopted assumption in terms of the texture and the interaction mechanism between the robot and the manipulated object is what we call fixed point contact, or FPC for short. So as shown in all these figures, the robots always climb or grasp the object, or they're fixed together by other facilities like ropes. Although fixed point contact is a simple and useful assumption, in many cases, it becomes restrictive easily due to its common limitations. For instance, its payload capacity is usually very limited, and the contact adjustability is also very poor. Once you have fixed it, you can't change it. So as a result, it becomes infeasible in many real-life applications, and we have to revert to non-fixed contact minus, or NFC for short, which is also hasn't been well investigated so far. So actually, in 2019, our lab developed an instrument for organ traction, which was compatible with the dVRK platform, and the low fixed contact was involved. So it was an early exploration, an example of non-fixed contact manipulation of deformed objects. But it's mainly in the mechanical design and the instrument control aspect. So in this work, we moved to the manipulation, autonomous manipulation aspect. So compared with fixed point contact, non-fixed contact enjoys significant advantages like increased payload capacity, better contact flexibility. However, we need to add the extra core parts in order to make use of non-fixed contact in manipulation tasks. So there are 2 key problems. The first one is the contact condition calculation, so that we know the real-time contact status. So the second one is its active adjustment strategy. Since when the contact condition becomes bad or unqualified, the robot should be able to make adjustment so that it can regain a good contact condition for the manipulation. Besides that, we have to integrate the adjustment of contact and the deformation control usually involved in deformed object manipulation tasks together. Okay, for the first question, so to describe and quantify the contact condition in non-fixed contact, we propose a novel 2-level description method. So specifically, the local level contact characterizes whether a valid physical contact is built between the end effector and the object based on the boundaries distances to the object. And the task level contact is used to describe, it's realized by the task-oriented context index we propose in this work, which takes account both the virtual features Jacobian and the feedbacks and the end effects influence on the feedback points. So actually, this Jacobian is used to describe the feedback points. The feedback points influence on the feature we are interested in, and the placement of the end effector is described by W. So, and we multiply them and get a product. We calculate the norm to describe the we say the effectiveness or the quality of the placement of the end effector. So this is a very simple simulation in 2D space considering an angle feature. So the red segmentation represents a plan end effector. So it can be serialized when the end effector traverses at the bottom of the object. The index varies significantly, and a large index usually indicates an effective placement of the end effector to manipulate the object in the ongoing task. So we have simulated two different configurations of points distribution and end effector sizes, and the results are also intuitive. Then we formulate the contact adjustment problem during the manipulation task in an optimization form, which tries to maximize the index we propose while respecting the local level contact constraint and the extra constraint that could be described by the feedback points. So the reformulation is in a quadratic programming form. The constraints are not irregular. So to address this, we use hierarchy strategy to get the optimization solution. So first, we try to adjust the global level constraint, and then we adjust task level contact, and finally, we adjust the local level contact. So this also makes use of the fact that the local level constraint need to be relaxed when adjusting high level constraints. Thus, it gets optimized at last. And besides, adjusting the local level constraints has little influence on high level constraints. So in each hierarchy, we can use a very classic method to optimize a single object function, like the gradient descent method. So for deformation control, the virtual feature is used to describe the deformation we are interested in, and the geometric potence method is modified to update the deformation manipulation Jacobian. So conventionally, when the object manipulates the object, it uses this commercial instrument like a forceps to grasp the object. But in the experiment, we use a 3D planted plastic plan to manipulate the object, which means that the contact can slide or can vary in the process. So this block chart shows the holistic control framework proposed in this work to combine the information control and the active contact adjustment. So simply speaking, according to the real-time contact condition, the robot decide what actions to take in the next step in order to finish the final manipulation target. So whether to manipulate the object or whether to perform contact adjustment motions to adjust the contact states. Okay. So finally, we show some experimental results. So in this experiment, it's very easy. So the robot just needs to manipulate the whole object so that the feedback point can reach the desired region. And we can see that during the process, actually the target, the contact stature changes during the task. And there are some trajectories and data. So this is for single point. And this is for the angle feature composed of 2 or 3 points. Oh, okay, this is red. It can be seen clearly. Sorry. There's some data. So, and following videos mainly show some contact adjustment process in the task. We can see that before the manipulation starts, the robot will rotate a little bit to establish a valid physical contact or slide along the object to reach a qualified placement and then start the manipulation. So this is for the single point feature. And this is for the angle feature. So it first slides a little bit or rotate a little bit and then starts manipulation. Okay. This is a little slow, actually. Okay. So in summary, in this work, we have composed a lot of characterization method at both physical level and the task level, presented an optimization-based formulation for active contact adjustment program and a hierarchy adjustment strategy. So at the last, a holistic country framework combining both deformation control and contact adjustment control is reported and evaluated by our experiments. So in the future, we think that we would like to extend this work to a 3D virtual system and explore more effective compilation manners of the deformation control and the active adjustment of the contact, because currently they are relatively independent. So, okay, that's all. Thanks for listening. If you have any question, please feel free to ask me.
Great.
Okay.
Thank you, Jing, for a great presentation and for staying on time. So we have time for questions. Maybe I should have mentioned this before, but for questions, please either type them in the Q&A or raise your hand, and then you can you can ask it live. So while people are thinking of their questions, I'll start with one, which is, as sort of a future work, are you also thinking about looking at the friction between of the contact? Because if you move in certain configurations, it may slip off, for example.
Yeah. But I think to take account of friction would be a little hard if we just use a virtual feedback. So in that we have to embed it, for instance, false information. But currently we mainly rely on virtual feedback to characterize its context issues. So it will be hard for the friction to be considered.
Right. Okay.
Yeah. Thank you.
Other questions, either from I guess people on the panel can just also ask, or again through raising a hand or Q&A. Okay. Well, again, thank you for the presentation. I don't see anything on the Q&A, but it's right about time to introduce the next speaker. Next talk will be given by Melody Su and Hedi Zhang from Mount Holyoke College in the US. And I believe Melody is going to start.
Hi, everyone. So I'm Melody from Mount Holyoke, and I'm going to play this pre-recorded video by my student Hedi, who is the main contributor for the project, but unfortunately is not able to join us today. So I'm just going to share my screen now. Okay, and okay, there we go.
Hello, everyone. My name is Hedi. I'm very happy to be invited to present our studies in this symposium. In our study, we use deep curiosity-driven learning to conduct multi-camera 3D viewpoint adjustment for abdominal minimally invasive robotic surgery. In this presentation, I will first introduce the purpose of our study and give some basic background knowledge. Later, I will explain our data generation and methodology, followed by my discussion on the results. Finally, I will give the conclusion followed by the references. As the title shows, our research interest rooted in the area of robotic minimally invasive surgeries. In order to help you better understand the scenery, we created this 3D picture. The green curvy line here represents the abdomen of the patients. The dark brown thing lying under it is the organ, and the middle black line represents the surgical tool utilized by the doctor to perform some palpation tasks on the tissue. So because usually in the surgical environment, the area in the middle is very dark, we need to employ those robotic cameras represented by those green triangle things. And in our study, we hope to help those cameras to maximize the visible coverage of the surgical scene and prioritize examining the surgical tool area simultaneously. We also hope to limit unnecessary camera motions, and while encoding this environment information to the model, we hope to simplify the state representation as we can. Fortunately, there already exists an advanced technology called multi-view autostereoscopy display, which can help us install those devices into human beings' bodies, and those things will be attached on the abdominal line. But what still remains to be studied is what software algorithm should we use in order to achieve the goals, as I mentioned before. In our study, we gained inspiration from curiosity-driven reinforcement learning. Curiosity-driven reinforcement learning is a sub-branch of reinforcement learning. In reinforcement learning, basically, one agent will interact with the environment, and by reading the state information and reward information generated by the environment, after every time an agent takes a step action, the agents will gain some information, and in general, it will produce an overarching policy that can help you to maximize the overall rewards. And for the curiosity one, we have a new element, curiosity. So there are usually two ways to define curiosity. The first one is by novelty. So if a state is harder to encounter, is novel, is rare, then it has a higher curiosity reward. And the second one is the prediction error, which is the one utilized in our study. So it means an area in which by taking the same action, the next state is harder to predict, will be associated with a higher curiosity reward, or we call it intrinsic reward. Put it mathematically, the intrinsic reward equals to the predicted value of the state at t+1 minus the actual value at t+1. In order to generate the data, in order to convert the 3D scenery, in order to convert the real sceneries to our to the environments that can be put into the model, we use a simulation procedure, and we convert the scenery to a sequence of 1,000 frames. Each of it has 30 hertz, and both periodically deforming abdominal wall and tissue surface and the tissue indentation from surgical instrument palpation are captured in this model. Again, our research objective is that given this scenery, we hope to find an optimal sequence of actions to move cameras such that the area seen by at least two is maximized while taking curiosity area, which is the tool area, into consideration. So in order to help our model better capture the crucial information, at the same time prevent it from being confused by overwhelming details, we further convert the 3D model information to 2D images. The 2D image can be represented by a two-dimensional matrix whose number of columns and rows are in alignment with the width and height of the image. And in each entry, one pixel of RGB channel values is sitting inside. The red channel values tells us the overlapping region information. So the higher the channel value is, more cameras are concentrated in that light spot area. And the green channel tells us the proximity to the curiosity area. The higher the green channel value is, the closer that pixel is to the curiosity area. And the blue channel value is also very important because, as we can see, a single light spot can be coming from the cameras on the upper right, or it can be coming from the one on upper left. So we use this blue channel value to distinguish those two situations. Another important things required to be done is to encode the action space of the agent, which is the camera. In our design, the camera can have 9 moving options, which are listed in this table. And each, since there are 3 cameras in total, and each of them has both x-axis and y-axis, in total there are 2 times 3 equals to 6 entries in this action space vector. So every time a camera makes its movement, we will update this action space, and later this information will be used to calculate the reward. One of the biggest contribution we made to the algorithm is by designing the reward. And in curiosity reinforcement learning, we have both extrinsic reward coming from the environment and the intrinsic one. The intrinsic one is coming from the intrinsic in curiosity module in our study. In this ICM model, we have both the forward model and inverse model. The main takeaway is that the output of the forward model will be used together with one intermediate output from the inverse model to calculate the intrinsic reward, which is the predicted one minus the actual one. And the extrinsic reward is coming from the environment. Basically, we go through each pixel to read their RGB values, and based on the values, we will assign different values to that pixel and divide it by the number of pixels in total. And we also have a second term, which tells us whether the single pixel is sitting inside the broad curiosity area or not. And we divide it by the area of the light spots, the shades. In our training phase, we use A3C for policy learning. The biggest advantage of this method is that we can train workers simultaneously, and they can share their current status with each other to work together to find an optimal solution in a most efficient way. So now it is our experiments phase after building those environment and algorithms. In our study, we have 6 experiments. The first 3 are the curiosity ones, denoted as AC1, 2, and 3. The number 1, 2, 3 just represents the number of channels being used in state representation. For comparison purpose, we have baseline approach. The first one is the static cameras, meaning cameras are not moving at all. The second one is the random one. And the last one is the Q-learning driven approach, which is coming from our prior work. In that work, we use Q-learning algorithm, and we represent the state by a long concatenated array of XYZ points in the 3D environments. So now let's see our exciting results. Let us first read the extrinsic reward. And clearly the blue lines representing the curiosity-driven lines outperform the blue lines, which are the baseline approach. And among the blue lines, AC1 performs pretty good in the beginning, but the rewards drops later on. And the AC3, the 3 channel ones, has very volatile extrinsic reward at the beginning, but the performance picks up later on. There is an interesting wavy pattern requires more investigation, but our guess is that this oscillation may due to the oscillation of the abdominal wall. In this slides, we can see the camera's abilities in tracking the surgical tool. The first line is the x-axis, the second one is the y-axis. Surprisingly, our third approach, which is the Q-learning one, performs the best, but our AC3 one also performs decently in tracking the tool. After talking about the extrinsic reward, let us look at the prediction error, which is the intrinsic reward. Recall from before, our action space has 6 entries, and here the 6 values in the x-axis means, so the 0 means 0 of these values are updated. 6 means all those values are updated. Not surprisingly, if we don't move cameras at all, the prediction error, the intrinsic reward is pretty low. And the main takeaway is that for the AC3 one, as we can see the purple line indicating its median value, tells us that by having more information being ready for the agents to learn, the lower the prediction error is, which makes a lot of sense. However, we won't choose actions based on this output because this is just the intrinsic reward. In our study, there's a trade-off between the extrinsic and intrinsic. This slide shows the reconstructability or visibility of our 6 algorithms. The last one, the AC3 one, performs the best as it can capture most of 3D points. And after taking weight into consideration, the last one, the AC3 one, even performs better. Here, the importance weights are allocated based on the distance of any point to the tooltip. This slide shows you the demo videos, and the first one is the red channel one. The second one is the red and blue, red and green. The last one is the 3 channel value ones. Before making a conclusion, let us recall our research goal is to find an optimal sequence of actions to move cameras such that the area seen by at least 2 is maximized while prioritizing moving toward the surgical tool area. In summary, the curiosity-driven reinforcement learning algorithm is indeed very good compared to other baseline approaches. And by encoding fewer information in the state representation is helpful for the agents to learn at first, but its performance will decrease later on. And having a more holistic state representation will confuse agents at first, but is beneficial for the agents to learn about the environment and make decisions overall. That's all about our presentation. And here's the reference page. If you have any questions, please feel free to reach out to us. Thank you all for listening.
Great, thank you. I guess let's convey our thanks to Hedi for a nice talk, and now you're on the hook for answering questions. Again, as before, if people have questions, they can put them in the Q&A or click the raise hand. I guess I'll start with one. When you were looking at the coverage, basically of the, I think of the surface of the organ and positioning cameras for that, were you considering also obstruction of the tools at that stage or not? Like if the tool obstructed part of the surface?
Not obstruction, but we did consider occlusion. So if the tool shaft itself is occluding part of the tissue based, yeah, from the angle, but no, not the obstruction though.
Well, I meant occlusion mainly. If it was blocking, if it was blocking the view. Yeah. Okay. Then, so you are considering that. Okay.
Yeah, yeah.
Well, that's so you can move the camera around. Great. Another question I had on the, I saw the blue channel was the rotation angle. Was that basically trying to encode something like the baseline, like how far apart the cameras were so you could get better 3D reconstruction?
Right. So the idea is, so if a camera is like looking over here versus looking over there, the viewable region will all look sort of like an oval shape and they could look exactly the same. But then by encoding how far away each of the point is from the camera, we can sort of get a sense of which one it is, whether it's looking from this way or that way.
All right. No, I guess when I assumed you meant by the rotation angle the relative rotation between the two cameras. Is that correct, or was it something else?
Yes, or it could be kind of looking at the same region of the tissue patch, whether the camera is looking from, let's say, the left or the right, based on kind of the distance from the camera. Yeah.
Okay. All right. Great. Any other questions? We've got about another minute if anyone wants to either put something in the Q&A or raise their hand. Yes, we have one.
Yeah, I was just wondering, is there any way to use like 3D reconstruction error as a kind of reward instead, or is that very like challenging? Because I think at some level there's also this idea that different viewpoints have different amount of quality that they can maximize depth perception and things like that?
Mm-hmm. Yeah, that's a great question. So I guess ultimately the goal is first, or hypothetically, it will be the goal for us to use those multiple cameras to do 3D reconstruction. And so we haven't actually gone to the stage yet. The idea of this project is more like, okay, so assuming each of those camera is just a monocular camera, so none of those are depth camera, what is the percentage of points that can be seen by at least 2 cameras, which will be kind of the prerequisite for us to be able to 3D reconstruct those points. But then, yes, that's a good point. So at some point, we will hopefully be able to also build this real-time 3D reconstruction algorithm and then use that directly as a reward to help us even better navigate those cameras. So yeah, thank you. Okay,
great. Thank you. And so I'll move on to the next talk where I'll introduce the person who just asked the question, which is Zhonghei Chua. I'm sorry if I didn't say that correctly, from Stanford University. So I'll turn it over to you now for your presentation.
So yeah, everybody. Hi, I'm Zhong Chua from the Collaborative Haptics and Robotics in Medicine Lab at Stanford, led by Alison Okamura. And today I'll be presenting some new results from our latest study to characterize haptic force feedback from multimodal neural networks in teleoperation of our DaVinci research kit. So force estimation is an important skill for performing safe procedures in robot-assisted minimally invasive surgery. And one way we can easily do this is to render haptic feedback for the surgeon. And indirect force estimation through data streams such as robot state or endoscopic images is one such method for deriving the forces that we can display to the surgeon. Of the methods proposed for indirect force estimation, I think neural networks have recently gained a lot of interest in the community. And many of these methods have relied on offline evaluation to judge the accuracy of the methods. I think only recently have there been attempts to test these methods in real time and with human-in-the-loop haptic feedback. One of these works was the one performed at Johns Hopkins, where they did pilot human subjects tests on force feedback to discriminate some sort of tissue stiffness. And for our latest study, we actually hope to build upon these kind of promising results and contribute more to understanding what happens in real time. Specifically, we wanted to probe the impedance transparency of model architectures, especially from our own previous ICRA 2021 paper. And by transparency here, we mean the extent to which impedance of the tissue or environment is accurately presented to the operator at the surgeon console. And we can do this first by considering transparency of the network in isolation, open loop, and then move on to the key question, which is what happens when you place the human operator inside the feedback loop? Does this affect the transparency of the impedance displayed? And also what are the stability, what's the stability behavior of the system? And lastly, I think we're interested in seeing, given what we found in question 2, are there any ways to address the issues of 2A and 2B? And here we predict that one simple or easier, I would say, way would be to quickly retune the network parameters with the data generated with the human in the loop. So to perform our experiment, we first begin with the model architectures from our ICRA 2021 paper. And this consisted of a vision and robot state model, which takes RGB image and a vector of robot kinematics and torque information from a single time point and outputs force prediction. And we also looked at the variant that only has unimodal input, so state only or vision only. And as a baseline, we implemented a adapted this physics-based dynamic model. Our models were trained on the data set from our ICRA 2021 paper, which consisted of these different viewpoints and robot configurations used to do the training of the networks. And we also use that same setup from the paper, which consists of using only one of the cameras with a crop view and a custom platform to mount the silicone with a force sensor underneath to get the ground truth interaction forces. So for the first experiment, in which we quantify the real-time impedance transparency of the networks without the human in the loop, we chose to do a palpation and tension or retraction task in the vertical direction, as we felt that this was an intuitive and commonly used maneuver to discriminate tissue stiffness with an interpretable result, namely a force displacement curve could be constructed. So we created a minimum jerk trajectory generator to provide the desired velocity, and then we rate controlled our dVRK to track the velocity profile and interact with the mock tissue, and then use the force estimator, the 4 kinds, and then the force sensor FS is the ground truth to get our force estimate. So we did this for the 5 conditions, 3 times in palpation and 3 times in tension over 3 samples each. And next, for the human in the loop experiments, we decided we would attempt to perform maneuvers in a single Cartesian direction and only provide force feedback in that direction, as we felt that this would enable us to look at the transparency and observe the stability behavior in each direction, Cartesian direction, without any coupling effects. And so we start with the same kind of minimum jerk trajectory generator and produce minimum jerk movements in the positive and negative direction of interest, holding each extreme position for 2 seconds each. We feed the desired position and velocities to our simulated human plant, which includes this position tracking and velocity tracking term, where the velocity tracking term was only active during the reaching phase and not during the holding of the extreme points. And together with the natural damping term from the human arm, so to speak, we produce the control force that generates the movements, of which we use rate control and also motion scaling to move the patient side manipulator to manipulate the environment. And then we close the feedback loop with our one of the force estimators. To try and quantify stability in this system, we look to using passivity, and the passivity observer and controller module was added to the system, and then we measured the amount of control effort the passivity controller was attempting to generate to try and passivate the system, of which here we only looked at the control side, the human side stability, passivity, so to speak. So we did this for the 5 conditions with and without the passivity controller in each of the 3 Cartesian directions. And yeah, for 3 samples each. So it's just like pull and hold, and then go to the other side, pull and hold. And then for the last part, to test our hypothesis about retraining, we took new data to augment the old data set. The first data set we took was one with only these slow kind of movements that you saw previously without force feedback given to the person teleoperating the robot to do those movements. And then second, with force feedback from the force sensor, which is this would mean it's the ideal force that we could render to the operator. And then lastly, with one of our pre-trained force estimation networks, namely the multimodal one, the VS network. And then we took only a subset of the data from our existing data set and then augmented with the new data set such that the contribution from each would influence the training process equally. So for the first experiment on characterizing open loop transparency, we can qualitatively look at how we can replicate the ground truth stiffness, which is this black line here, which was from the force sensor. and we want to look at and see how close we can get to it. So one thing we note is for the state-only network, we did realize that there was this quick unloading during palpation that we think might be due to some kind of overfitting to the state inputs. And we know that the multimodal network, we think best replicates the shape of the force displacement curves, though there seems to be some kind of bias inherent in the estimate. And then for the vision networks, intuitively, we see that it doesn't really capture very well the increased stiffness of at high displacements. And we think this is likely because there's much less visual force information at high displacements. And so it's not playing to the strengths of vision-based kind of force estimation. So for the human in the loop experiment, we thought we could see that trajectories of force and displacement can kind of provide a useful overview of the transparency and stability behavior. With the force feedback being the blue, force sensor, the ground truth being the purple, and displacement being the green. And for here, we can see that with the our state-only network, there are large oscillations. So, and also for the multimodal one, there are large oscillations that also spill over to the displacement in X and Z, with the vision state also having some of these oscillations in the Y axis. And then for vision, what we see is that there are none of these large oscillations, but we get poor transparency in palpation, which are these portions here, well, the negative Z translation, and then also poor transparency in the Y direction due to a lack of depth information, we think, in that direction from the camera. In terms of refitting, we see that refitting with force feedback, which is these two conditions over here, does reduce some of these oscillations, especially the one which we gave the data was from feedback from our existing force estimator. In X, Y, and Z, we can kind of see this. And then we also know that, just training with the force sensor alone also helps reduce these kind of oscillations. More quantitatively, we can look at transparency with the root mean square error of the predictions. And we see that, refitting in general improves transparency, with the estimated force feedback data being able to, fit the parameters such that we reduce the error the most. So it's this pink one. And then for stability, the average control effort during the extreme holding positions, we see that the refitting also reduces the amount of average control effort. And we think that this is very prominent in X direction, but less so in Y and Z, mainly because at some point, if the oscillations are small enough, the human hand manages to damp out a lot of these oscillations, though whether it feels good or not is a different story. So in summary, we think we can say that the vision-only feedback seems more resistant to the disabling oscillations, but suffers from poor force transparency when visual information is low. And then the vision state feedback, it seems to perform more consistently than the single unimodal one, and benefits from human in the loop training data. So we think that future work could involve some user studies, because ultimately that's the most important thing. Does it improve performance even despite less than perfect transparency? And given the vision's promising, I would say, robustness, so to speak, maybe that's the wrong word, but to the oscillations, we should try and fix this problem with the lack of visual information by maybe leveraging the stereoscopic views. And lastly, we haven't looked at the recurrent architectures, and we think that they have different kind of dynamic properties from such as our static model, and we think that perhaps we can explore those further. Thank you.
Great, thank you very much, Bong-Hye. We're open for questions. I think we have time for maybe one question. Again, type something in the Q&A, and feel free to type questions in the Q&A during presentations in the future as you think of them, or raise your hand. So any questions from participants? So I think this is very interesting work. And oh, I guess Blake, okay. If people are having trouble putting things in the queue, I haven't tried, but I just got a report that there might be trouble asking questions. Maybe it's only for the panelists. I don't know. But please raise your hand if you can't put something in the Q&A.
Yeah, I think for the panelists, we can put it in the chat as well. I think
Panelists can put in the chat. Okay. All right. All right. So if you're not a panelist, to put in the Q&A or raise your hand. If you're a panelist, I guess raise your hand or chat or unmute. Okay, Blake, I see you have a question. I think you're muted, Blake.
Sorry, I was typing it into chat.
Oh,
I'll type it in and it'll be ready soon.
okay.
I think I'm ready for a question.
Okay, why don't you go ahead, Anton, and
Okay. So
we'll...
in one of the first pictures, it seems like you're doing the palpation with the PSM all the way from the side. So the most of the pressure will be done and measured from the first joint on the PSM. Most of the studies that I've seen so far, I've been taking advantage of the translation stage to kind of do the palpation. Did you study both? And is there one that is nicer to work with than the other?
Yeah, I think we collected most of the data from that. Yeah, with the rotation pretty far out. We did do some in our previous paper with it closer and more using the translation. But yeah, I think we haven't explored the different configurations, which is really good, a good idea for the following up on these results. We just really wanted to see what we got from the first pass, given our experimental setup. But I think there could be some implications of using different joints, more relying on certain joints more so than others.
Yeah. So now Blake's question is, was there a pattern in passivity observer output with the different methods?
Yeah, there definitely was. I think the main thing here was how frequent the passivity controller would like switch on, because it only switches on when the energy is like negative. And I think the main thing was with the dynamic or the physics-based model, because we kept the damping coefficient for the controller, it usually saturates out and like it tries to bring it across to passivity, but doesn't. But for the others, I think the only difference was with the force sensor. We also ran it with the force sensor, and like there's just a lot of low-level noise because of the high update rate, and so it like just switches on a little bit here and there. And then for the others, I think it bursts for a bit and it kind of brings it down, and then it starts to go a little bit unstable again, and it just bursts up and down like almost like an EMG. Yeah, that was about what I saw.
All right, thank you. Let's move on now to the next speaker, who is Kim Schwanner from the University of Southern Denmark.
Yes, thank you a lot. Let me just share my presentation. There you go. I think you should be able to see it now, right?
Looks good.
Great. All right, thanks. And thanks to the previous speakers for nice presentations. I'm Kim from the University of Southern Denmark, where I'm a PhD student with Professor Rajit Savrimutu. I'll be giving a talk today entitled toward autonomous suturing using MOPS, a modular and open platform for surgical robotics research. And in this talk, I'll tell you a bit about some work we've done on automating surgical tasks using the suturing task as an example. In my work, I've used both the Raven and dVRK platforms, after which I ended up developing our own surgical robot system for research. And this system that we came up with, its applications and the reasons for its development will be kind of the focus of this talk. So to give you a little bit of background, we have this overall vision for future surgery, which is driving our work. Basically, we envision the robot as an apprentice to the surgeon. And from that apprenticeship, we can construct a library of surgical actions which can then be used to facilitate autonomous execution at a later time. So in my work, I've been taking a very, say, practical approach to this. I've been wanting to see things work in real life. And in some of my early experimental work, I used the Raven platform, which we have at SDU to evaluate my methods. I tried extracting, say, surgical actions from the Jigsaws dataset, as you probably know well, many of you. Even though this didn't contain camera intrinsic parameters or robot and camera calibrations. I noticed during this work that beside the relatively poor state estimate of the Raven, it was also exhibiting pretty poor trajectory following performance, and we did some work to improve that. But still, the work was not very impactful considering the state estimate errors themselves. So all in all, I guess you could say my attempts to automate surgical tasks using the Raven was not very successful. Now, I had the chance to visit Paolo Fiorini's lab at University of Verona. Here I got to use the dVRK that they have there to further try automating this suturing task. This time I extracted surgical actions from a dataset similar to Jigsaws, but including camera calibration, a dataset recorded at University of Verona. And this figure here, this figure here shows the system or the experimental setup that I use, where I attempted autonomous needle pickup and insertion, and these attempts were moderately successful. So this is kind of an example from that. The top row is demonstration data from the dataset, and showcases some steps in the task. The autonomous execution is the bottom row. The task was quite successful in the sense that we could generalize to differing initial conditions using stereo vision for detecting the needle pose and the insertion points. And I say only moderately successful because the needle did actually not fully pierce this fabric surface that we use, both because we painted the needle such that it was actually quite dull, and the fabric was very pliant. But anyway, after getting back from Verona, I and having these attempts with the dVRK being moderately successful, say, I learned a lot from that. So at this time, I had concluded that the Raven was probably not going to give me satisfactory results for this kind of task automation. Also, we didn't have a dVRK at STU, unfortunately, and probably we were not going to get one anytime soon. So I instead decided to set up an alternatives custom robot system. And the result was this here. So this is kind of what we came up with. UR robots with custom adapters for mounting and actuating standard surgical instruments, a custom stereo camera rig, and a, let's say, poor man's surgeon console. So using the system, I was able to fully automate suturing needle throws, including needle pickup, grasping, insertion, extraction, and needle handover in a bimanual suturing task that I will just show in this short video. There we go. So this was system overview. This is demonstration data recorded with the same platform. And then subsequent autonomous execution of that task, where we generalize the task to differing initial conditions. That is the initial location of the needle and the insertion points. So these are different task conditions. It didn't always go as we wanted it to. So here are some failure modes. Mostly the tasks failed due to wrong or poor state estimate based on the visual feedback. So that is needle pose estimation and estimation of the insertion point locations. Nonetheless, with this task, we obtained over the course of 46 trials a success rate of about 36% for the full task, including the needle handover from one arm to the other. The mean subtask success rate was 75% of all the subtasks put together. That is insertion, extraction, handover. The mean needle insertion error was about 3.3 millimeters over the course of all the trials. So fairly precise insertion, despite many sources of error possible in the system. So this is kind of an overview of the system that we built. In our case, it consists of these UR robots with surgical instruments, as I mentioned, cameras, PCs for robot control and vision processing, and the surgeon console made from these touch haptic devices, and a regular monitor displaying a left-right red cyan anaglyph. Here on the right side are 3D renderings of the adapters that we built for mounting and actuating the surgical tools. Basically, these consist of 3D printed parts and servo motors and gears and belt drives for actuating the joints. So this is what the system currently looks like in our lab. But the robot arms, input devices, or sensor systems, even the surgical instruments could be exchanged with different hardware. And for example, the UR robots could have been a KUKA robot, or say a Panda robot. So we have these hardware components and a number of software components for putting it all together. And we've named that MOPS, a modular and open platform for surgical robotics research. Modular because it's, well, modular, and open because we are making it available to the community, and hope that you guys can benefit from that too. So just to emphasize some of the benefits of such a system, similar systems can be built from different hardware using what's available in a given lab. Hardware components can be exchanged relatively easily. It requires only modifying the robot model and driver software for those components that you change. Again, we are making this available to the community. We put it, the source code and design files in the repositories in the link below. And I hope that if you're interested in using this project, that you will contact me or consider contributing back any changes you make. We are currently collaborating with people at the Jožef Stefan Institute in Slovenia in the group of Aleš Ude to set up a similar system there based on KUKA robots. So some future work we could discuss with this is, well, in the spirit of this symposium, integrating with the collaborative robotics toolkit, I think is definitely one to look at. It's not something that we have done yet, but just considered the ROS implementation, or we use ROS for all our software components and for the inter-component connection and communication. So it should be a fairly simple task to integrate with much of the CRTK API. We also plan to adopt ROS 2 soonish. Plan to improve perception. So currently, in the suturing task, for example, we rely on color-based segmentation for detecting needle pose, for example. Also, we plan to integrate additional sensors into the system. So one advantage of using this kind of system is that you can more easily, I would argue, integrate more sensors into the system. And for example, the UR5E robot that we used for one of the manipulators in our setup, it has a force sensor in the wrist already, which we can use and which we have used to for contact detection, for example. Also, we'd like to extend this surgical action library concept, which is really rather simple so far. And finally, this a small advertisement here. So I omitted a lot of details in the, especially in relation to the automated suturing task. And these you will find in some forthcoming papers, which are here, accepted to CASE and IROS. And I also submitted a paper detailing the platform that you just heard about to ISMR. If you're interested, look at this website and please contact me again. Things are still a little organized or disorganized, as you would say, in these repositories, but I hope that it can be better soon. And with that, I'll conclude my talk. Thanks for listening.
Okay, thank you very much for your presentation and for your contribution to the community.
Thanks.
Yeah, I think we have a minute or so for questions. I see there's one in the Q&A. I don't know if that's for this. Yeah, for this talk. Can we do stereo reconstruction firstly?
So I think the answer depends on stereo reconstruction of what. Currently in the suturing task, it's very sparse stereo. So reconstruction of only, sorry, of only points belonging to the suturing needle and points belonging to the insertion points that we marked with a pen or marker on the phantom tissue suturing pad.
Mm-hmm.
So
Okay.
there's no dense stereo involved here.
Yeah. Yeah. I mean, maybe the motivation for the question was that I think you pointed out, quite correctly that systems like the dVRK and Raven, their strength is not in their accuracy or their trajectory following, and that
Right.
when they're used by humans, there's this visual loop that's closed, and
Indeed.
I don't know if you in your setup, was it sort of a one-time location of the entry point, or were you also trying to do like a closed loop when you were doing it autonomously, that is, doing like a
Right.
visual? Did you try that?
So this is a closed loop in the sense that we detect the insertion point before the actual insertion happens.
Mm-hmm.
So if you move the suturing pad while the robot is moving, it will not adapt the motion to that. But
Okay. Yeah.
if you move it as an initial condition for the task, it
Right.
will adapt the motion to that.
Okay. Yeah.
So yes, closed loop in
That, yeah, but
in that
it's right.
sense.
Yeah, and that's why I think that's one of the reasons you also need good accuracy of the robot, because the other
For
use
sure.
of servoing might be to correct for robot errors. But, okay, well, still very very interesting work. And I look forward to taking a look at your platform and maybe talking more
That
offline.
would be great. Thanks.
Are there other questions from anyone else? I think there's another one that popped up on the Q&A. Oh, just a thanks. Okay.
Sure. Thank you.
All right. Thank you very much. We'll move now to the next presentation from Juan Antonio Barragan, who just finished his master's at Purdue University, and will soon be joining us at Hopkins. So I'll turn it over to you now, Juan.
Quick second. Okay, are my slides showing right now?
Yes.
Good, perfect. So welcome everybody. My name is Juan Antonio Barragan. I'm a recently graduated master's student from Purdue University, working in the School of Industrial Engineering with Dr. Juan Pablo Wax and Dr. Nayib. And today I'll be presenting my work, Controlling Cognitive Demands with Semi-Autonomous Action Framework for Robotic Assisted Surgery. I'll start talking a little bit about the operative workload in robotic surgery. Might be a little bit redundant to this audience, but so usually in robotic surgery, we'll have the leading surgeon teleoperating the surgical robot from a console outside the stereo area on the OR. And on the patient side, we'll have one or two surgical assistants. They'll be collaborating with laparoscopic instruments with the leading surgeon and some other support tasks, such as the docking of the robotic instruments, exchange of the instruments, handling of suturing materials. Among all the support tasks performed by the surgical assistant, blood suction is one of the most critical to maintain a clear surgical field, avoid infections and complications that can even force the surgeon to convert to open surgery. Traditionally, this task is done by the surgical assistant with laparoscopic tools. This way of doing it has the limitation that the surgical assistant is limited on the attention that it can give to other like support tasks. More recently, there has been the development of flexible suction tools such as the ROSA system that we can see in the slides. And these systems allow the surgeon to directly control the suction tool. However, this also results in increasing fatigue and cognitive demands during a procedure, which increasing the cognitive demands can lead to human error and worse reaction to an unexpected situation, which have a direct impact on the patient care and surgical care. To alleviate this situation, we proposed a autonomous system for the task of blood suction that can collaborate directly with the surgeon while he uses the main instrument arms of the robot to perform a task. So the design of our system can be divided into two different modules. We have the robotic or autonomous module, where the main building block is a computer vision system based on semantic communication networks. We have a very simple path planner to navigate a surgical field. And then we have a toleration site. It's basically like the surgical console where our user controls the main instruments to do a task, a training exercise. We deployed our system in the dVRK robot. The robot contains 3 teleoperable robotic manipulators and an endoscopic camera manipulator. This is an image of the robot that we have at Purdue University. For our experiments, we had the user controlling the PCM1 and PCM2 to perform a surgical task. And we had our system deployed on the PCM3 so that we had collaboration between the autonomy and the human, the user. Firstly, we perform a calibration procedure to find or register the tooltip of a PCM to the camera frame. This transformation is essential to transform between robot coordinates and image coordinates. We constructed this based on 3 different transformation matrices. The first one between the tooltip of the ECM and the camera frame was found with a hand-eye calibration procedure using the Kronecker product. This middle term is provided by the API of the dVRK. And finally, the transformation between the base of the PCM and the base of the ECM was found by using a chessboard, a calibration chessboard as an intermediate transformation. As a computer vision system, we developed semantic segmentation algorithms that were automatically trained to segment blood accumulations. The goal of semantic segmentation is to assign a label to each one of the pixels in the input image. For this task, we collected a data set of 150 images. From there, we got 188 or 148 for training. We used 10 for testing. Up to 250 epochs of training our algorithms, we got a training set accuracy of 95.3 and testing set accuracy of 96. This is the pixel prediction accuracy that I'm reporting right now. As a network architecture, we used a fully convolutional network based on VG16's architectures. Below, you can see a small clip of the endoscopic camera that was a simulator that we developed to test our system. On the right, we see the segmentation maps created by our computer vision network. In there, the red pixels represent the blood accumulations and the blue pixels represent the instrument arms. Then we used a transformation to calculate robot coordinates from pixel coordinates. To simplify a little bit our setting, we used a homographic transformation to calculate XY positions of the robotic manipulators. We used to calculate this homography, we use a simple calibration procedure with the markers, with the color markers shown in the image on the right. We also developed a simple augmented reality module based on OpenCV drawing capabilities. The goal of this module was to improve human-robot collaboration. This was a red transparent annotation that showed where the autonomous suction system was going to go, so that the user could plan ahead their actions. On deployment, the system calculated, segmented the images from the endoscopic camera, and then selected the biggest blood accumulation as the next target. In the video below, we see the user controlling the main instrument arms of the Da Vinci robot, while our autonomous system moved around to provide the blood suction. To evaluate the system, we had we conducted a user study where we compare the autonomy against a manual operation of a suction tool. So in autonomous condition, the user only controlled 2 of the arms, while the autonomous suction tool moved around the surgical field to provide the suction for the user. In the manual condition, we had the user swapping between the teleoperation of the main instrument arms and the suction tool, given that the dVRK only allowed to teleoperate 2 instrument arms at the same time. The protocol we followed for this study was we recruited 8 participants. They were engineering students from the school from Purdue University. We trained them in to perform a running surgery exercise. This was within user study, meaning both participants performed both of the conditions. And at the end, we performed 2 tests to analyze the statistical differences between the 2 of the conditions of our experiment. To evaluate our system, we had a combination of objective and subjective performance metrics. We had the main performance was measured by the completion time. We also used some kinematic metrics, such as the average velocity of the main instrument arms. We collected also some system events, such as clutching, number of clutching that the user had to do in both conditions, the average percentage of blood that was detected on the video, on the endoscopic video on both conditions. And then to evaluate the workload demands of the users, we gave them a NASA TLX survey at the end of the experiment. The main findings of our experiment was that our autonomous system led to a reduction of the completion time, again, compared to the manual operation of the suction tool. Users were able to perform the task 162 seconds faster. We also find out a significant reduction of the clutching events. So during the manual condition, every time the user swapped to use the suction tool and return back to the operation of the main instrument arms, they had to use the clutch on the console to re-accommodate the console manipulators to a comfortable position to continue the task. This didn't happen when using the autonomous system. We also saw a significant reduction of the percentage of blood detected, meaning our autonomous system was more effective at cleaning the blood in the surgical field than the user that was doing both of the tasks at the same time. Finally, you have a reduced workload score. The TLX has 6 dimensions that to evaluate mental demands. And at the end, you can have an overall workload score that represent the perceived demands in each of the conditions. So here, people was more comfortable working with autonomous condition. To improve our system, we started working on ways we could further improve the human-robotic interaction. So one of the main issues that we found during the user studies was the fact that some regions of our simulator created occlusion, such as the situation that we're seeing in the video clip on the right. This created additional mental demands and frustration for the user. We have been working into incorporating a surgical gesture recognition system such that the autonomous system can identify when the user is performing a critical step of the procedure and plan ahead when an occlusion is unavoidable in moments where the user is not doing a critical task. The other step that we have been taking to improve our system is utilizing more advanced augmented reality with OpenGL. So our idea is to have a full CAD model of suction tool into the surgical field, so that it improve the predictability of our system. Another direction that we've been following is using physiological analysis to estimate the workload state of the user in real time. In this regard, we've been working with EEG sensors and a tracker to estimate in real time the workload of the user and use this information to adapt the behavior of the autonomous suction tool. Basically, our hypothesis is that providing suction tool in the moments of most stressful situations can be beneficial for the overall performance and efficiency of the procedure. As a conclusion, we developed an autonomous suction tool for the setting of robotic surgery. We found that semantic imitation algorithms are effective to detect blood accumulations in real time for autonomy applications. We saw that our autonomous system has the potential to improve surgical performance and reduce cognitive demands, as well as improving the human-robotic collaboration fluency. Thank you so much. If you have any question, please feel free to.
Great. Thank you, Juan, and thank you for staying pretty much on time. We started your talk late.
Thank you.
We've got questions already, so I think we'll just do those two. First was from Blake. Were your p-values corrected from multiple comparisons? Did you assume that NASA TLX components were statistically independent?
Yeah, for our analysis, we assumed the statistical independence for NASA TLX. And unfortunately, we didn't do the corrections for the p-values. We use simple parity test, assuming given that the users perform both of the conditions.
Okay. Okay. Let's see. I think there was also a question in the Q&A from Anton. Did you use something like MoveIt to prevent collisions between the suction PSM and the other two PSMs teleoperated by the user?
No, that's still currently a limitation of our system. We didn't have any mechanism to prevent collisions. We tried to use some current feedback, some of the dVRK information that give us on the current to move the autonomy back in case of a collision, but it was very primitive. It was simple, like a safety mechanism to avoid a crash during the experiments.
All right, great. Thanks very much for all of that. Interesting work. So let's move on to the last speaker now, who is Dario Galeazzi, maybe, if I said that correctly.
That's right.
Polytechnic of Milan. So you're up now. Okay, can you see my screen? Yeah, it's not yet in presentation mode, but we can see it. Okay, now to presentation mode.
Okay. Thank you, Professor Katsanzides. And so I'm Dario Galeazzi, and today I'm here to show you the work me and my colleagues did at the Robotics Institute of Sant'Anna. And it is about learning and training with Da Vinci. And in particular, with our clinical partner, we worked on training for robot-assisted lung lobectomy. And this is the standard procedure, lung lobectomy, for the treatment of non-small cell lung carcinoma which is the third most common typology of cancer. And basically this procedure consists in the removal of the disease lobe. And this can be done by separating the lobe from both the circulatory system and the bronchi. This is possible thanks to this mechanical stapler, which is able to cut and suture at the same time those anatomical structures. So once all of them have been resected, it is possible to proceed with the removal of the cancer. And just to give you a picture of how these numbers are increasing, Da Vinci is being used even more over these years, thanks to the multiple advantages that it brings to the operating room. But one thing still strikes surgeons, which is the absence of haptic feedback. And in particular, in procedure like this can translate in excessive forces applied on tissues. In this example of lung lobectomy, it is reported that in 2.4% of cases, surgeons apply excessive tensions on main blood vessels. And this is very critical because it can result in the wall rupture. And as you will see now, it can result in a dramatic bleeding. And of course, this is not a fun situation to be in, neither for the surgeon nor for the patient. And so how do we stop this from happening? The main thing we have is training. So the surgeon, it is very important that he trains before entering in the operating room, and it is fundamental that he learns how to deal with the lack of haptic feedback. And this is the option we have right now as simulators. On the left, we have virtual reality simulation, which among all the advantages that they bring to the table, there is a quantitative and also an objective skill assessment of the surgeon's ability. And unfortunately, virtual reality is still afflicted by a low fidelity of robot tissue interactions. And but the realism of this interaction is really helpful to the surgeon, and it is fundamental to the surgeon to understand how to deal with the haptic feedback loss. On the right, we have a simple physical simulator, which is basically a mannequin, and it presents actually the opposite problem of the virtual reality. So good interactions between robot and tissue, but no data. So what we did at Sant'Anna was to develop a sensorized physical simulator in order to combine the advantages of the two. So we have high fidelity robot tissue interaction from the physical simulator, and also the sensorization can provide us data to give, for example, a concurrent feedback to correct online errors of the surgeon during the simulation. And also it can provide a terminal feedback for an objective skill assessment and the monitoring of the surgeon progress. So in the specific, for the lung lobectomy, what we did was to develop pulmonary vein simulator, which is one of the most critical parts, structures of the procedure. And we sensorized it with the goal of monitoring strain, which excess can cause the blood vessel rupture, and so the bleeding. And finally, we also did a user study to evaluate the utility of concurrent feedback and of the sensorization. And this is basically what we did. It was a very simple process, but I believe it's effective. We realized the pulmonary vein with the cast molding technique, starting from medical images and literature data. And we sensorized it with this textile sensor, which was very handy because thanks to its non-invasiveness, it was able to maintain the realism of the simulator. In fact, you can see the simulator on the left here. At this time, we were taking the characterization of the sensor. And finally, for the user study, we used the dVRK that we have at Sant'Anna. So we asked the user to perform a simulation of lung lobectomy that you can see on the right, which is mainly composed of these two steps. So the isolation of the blood vessel, and the second, the insertion of this stapler simulator, because unfortunately we didn't have a proper stapler, but this served as, let's say, as a simulator. And we gave concurrent feedback, both in a visual and acoustic manner, like in the operation game. And basically, threshold was, feedback was given when a certain threshold was overcome. And this threshold was chosen on the base of mechanical parameters of the real pulmonary vein. So this is a scheme of the experimental protocol of our user study, and 10 users participated and were divided in two groups that underwent different training pathway. The control group trained with no feedback, so doing only repetition of this simulator. And the experimental group did 5 repetitions with training. And in the end, both groups performed 2 evaluative repetition with no feedback, so that we could compare the outcomes of training. And this is the trend that we found in strain over time, and we can clearly see the 2 main steps of the simulation, so isolation and stapler insertion. And as evaluative matrix, we used this red area over the threshold S, called summary score, and also the maximum strain applied on the pulmonary vein. These are the results. As you can see, the experimental group in green and the control group started from a very similar condition, but you can see that right when we started giving concurrent feedback to the experimental group, it ameliorates quickly, and of course in comparison with the control group. But still, perhaps the most interesting thing is the fact that even when we removed the concurrent feedback from the experimental group, it maintained similar values that are also better to the control one. And similar results were found in the maximum strain applied on the pulmonary vein simulator. And as you can see, the experimental groups tended to apply lower tension on the pulmonary vein, both during training and after it, so during the evaluation. So we can make these 2 final consideration, which is the first one. The concurrent feedback led to an online reduction of tension on the applied tension applied on tissues. And the second one is the fact that training with concurrent feedback actually helped in learning how to reduce tension applied on tissues. And we believe this is very important because it could ultimately lead to a better education for surgeons, and in this case in specific, that of lung lobectomy, it could bring to a reduction in the bleeding incidence. And also on another note, the cost, the additional cost for the sensorization of the pulmonary vein simulator was very little, and we can say that in the end, the training with a sensorized simulator might be better than a simple than training with a simple physical simulator. As for future developments, something that we are already working on actually is about the comparison of our simulator with other methodologies of training, and we plan to do it also with an higher number of participants and possibly surgeons, so with a surgical background. And also we plan to do some mechanical studies on the simulator itself to study its high fidelity. And finally, the concept at the base of this work, we believe are valid also for other steps of lung lobectomy, but also for different kind of procedures. So we believe that further sensorized simulator could be developed always in order to achieve the better training for the next generation of robotic surgeons. So that is all for my presentation, and thank you for listening. And if you have any question, I'll be happy to answer.
Great. Thank you very much, Dario, for an interesting presentation and for, again, staying on time since we started a few minutes late. So we'll open now for a couple of questions. I think there's one on the Q&A, which is from Anton. Is the apparatus mounted on the instrument used for visual feedback only? If so, could you be using AR, meaning augmented reality, instead?
Yes, actually, we call it a band. When we mounted it on the instrument to give visual feedback, obviously, but unfortunately you couldn't hear it in the presentation, but we gave also an acoustic feedback, so there was a combination of the two. And also regarding the augmented reality question, yeah, it could be possible, obviously, to implement it on our simulator, but we stayed a little bit, let's say, grounded with it. We started simple, and because it would have been, let's say, another chapter. Anyhow,
Okay.
so multiple studies have been made also on augmented reality, and now it can, and if it, the fact that it can work better or worse than other kinds of feedback.
Yeah, well, I think the question was just, you're adding more complexity to have to introduce something with wires on the end of your Da Vinci instrument, whereas you could, if it's really just a light turning on and off, you could do that just directly.
Yeah, that was also an option. The fact that to just put a light near the simulator, we found out this. We thought it was good looking, let's say, and kind of easy to understand too. So the fact that every user understood correctly how to interpret the feedback, we believe was a success. Obviously, there are multiple ways by which you can give both acoustic feedback and, of course, visual feedback.
Okay, thanks. I see one more question that came in from Zhanghe. Was there any way for the control group to know if they were performing the task poorly? If there is no failure mechanism for users to detect, do you think that it would be likely there would be very little learning shown for the control group?
No, actually, there were no failure mechanism in the sense that the simulator wouldn't break and wouldn't spill blood. So yeah, but that neither happened for the experimental group. So I believe the only difference in the two pathway they underwent is the fact that actually experimental group had a feedback that warned when a strain threshold was surpassed.
Okay, thank you. I guess one quick question I had, did both groups know that the evaluation was going to be performed without the assistance, without the additional feedback? Well, I guess mainly not the experimental group. Like, did they know that, gee, they better pay attention and try to learn because they're going to be evaluated without the
No, none of them. No, they don't know that there were going to be. We did the same with time, actually. That we, okay. I didn't mention it, but we did the same with time. We didn't give the users let's say some parameters on which to base on the evaluation. So in fact, you can see that they all have a similar time of execution because nobody was in a hurry. But on the other hand, the applied strain, the applied tension on the simulator was lower for the group that trained with feedback.
Okay. All right. Great. Thanks very much, Dario. And I want to thank all the speakers today and all the participants for joining. And sorry we ran about 10 minutes over, but I hope everyone enjoyed the presentations. And my understanding is this is going to be hosted, I think, on YouTube by Hamlyn Symposium. So you can go back and look at it again. All right. So I think that's all. I don't know, Marianne, is there any thing we need to do to kind of close?
No, that's it. Nothing to make.
Okay. All right. Well, thanks all. Have a good morning, afternoon, evening, whatever your time zone you're in. All right. Bye all.